For this problem, it says we have an open feed water heater, and that is basically a direct contact heat exchanger that's going to be used in vapor power plants. The operating data for an open feed water heater with water as our fluid operating at steady state is shown. All right, so that's going to be important that it's steady state. We're going to ignore the stray heat transfer, that's important, from the outside of the heat exchanger to its surroundings, and also these two effects. We want to find the rate of entropy production in kilowatts per Kelvin. Remember, that is sigma. So that's what we're looking for. Now we need to get to sigma. So remember, the equation that we've got for sigma is the one where we're going to use entropy rate balance. Okay, so that's the equation we are working towards. Now, if we were to go through and write that out, let's see what that looks like. It's steady state, so it's going to be 0 on that left side. You'll have the sum of Q dot over T. Here we are ignoring all the transfer to the surroundings. That goes away. Then we're going to have plus M1 dot S1. That's an inlet. And then we're going to have plus M2 dot times S2. Again, that's an inlet. So it's positive. Now our exit, which is 3, is going to be negative. So we'll have negative M3 dot S3. And then finally you get your plus sigma dot. Actually, it's a sigma dot we're wanting, not sigma. Right, so sigma dot will be your rate. Now this is what we are looking for, so that means we got to fill in all of these details here. That's what we're going to be working towards. Alright, so to do that, we're going to have to use our tables. And now if you think about it, even if we use the tables right now to find these S values, do we know the mass flow rates? No. So we got to have another way to find the mass flow rates. For that, let's go ahead and we're going to set up another just regular energy balance equation. So let's look at the energy balance equation. So this is the entropy rate balance. Next, let's look at energy balance. That'll give us another equation that has m dot in it. Energy balance, we'd have 0 equals q dot minus w dot plus m1 dot h1 plus m2 dot h2 minus m3 dot h3. Now we've got that. W dot goes away. We don't have any power going on here. Q dot goes away because it told us to ignore that. Now we've got this expression here. Now remember that we also have steady state data shown, so that gives us a relationship between the mass flow rates. If it's steady state, then we know 0 has to be equal to m1 dot plus m2 dot minus m3 dot. That gives us that relationship as well. Now, looking at this, let's go ahead and let's solve this for m1 dot. m1 dot then is going to be m3 dot minus m2 dot. Now with this, let's plug it into here. So that allowed us to get rid of one variable here. We're getting rid of m1 dot by making this switch here. So we'll have 0 equals m3 dot minus m2 dot times h1 plus m2 dot times h2 minus m3 dot h3. Now we've got that. With this, let's go ahead and solve for m2 dot. m2 dot then, once you do your algebra, is going to be m3 dot times h3 minus h1. Put that over h2 minus h1. Now at this point, If you'll notice, the reason why we worked towards this is because we were given M3 dot, in case you were wondering why in the world I decided to go in that path. So now we've got this 80 kilograms per second, that's given, but we don't have these H values. We need to find the H values. So to do that, we're going to have to look in the tables, and let's set up a little diagram here so you can see where everything is. So this is a TS diagram. On this one, let's go ahead and draw this. So we've got 3 bar. Now for this one right here where we're coming in, we've got P1 is 3, T1 is 36. If you look that up in the table, you'll find that that's down here. That's compressed liquid. Now let's do the other two, and then we'll move on to the tables. Here you're given a quality of 0.92. If you got a quality, that means you're in here somewhere. Let's say that is state, or 0.2. And then finally on 3, we've got saturated liquid. If we've got saturated liquid, that means we're right here. Okay, so these 2 points, 2 and 3, you're going to use the saturated liquid table. Now 1, that's compressed liquid. Generally we can treat that as incompressible and just assume it is going to be like the saturated liquid point. Now keeping all that in mind, let's get our values. So for H1, that's that compressed liquid one, we're going to say that's approximately equal to the saturated liquid point at T equals 36. Alright, so you go to your liquid table, look up this temperature, and get the HF value. That'll be 150.86 kilojoules per kilogram. And while we're in the tables, let's go ahead and get the S values, because look up here, we're going to need those. For S1, you'll make this same assumption. We'll say that that is equivalent to the entropy at the liquid point at that same 36 degrees Celsius. That value is going to be 0.5188 kilojoule per kilogram Kelvin. State 2, in here we got to find the exact value, because the value right here at this point is not given at the table. We only have the values here and here. We're going to use our equation to do that. So H2 is going to be equal to HF2 plus the quality times Hg minus Hf. So Hf and Hg are found in the table. You've got that pressure given, so look up 3 bar, go to the right, find these 2 values. If you do that, you get 561.47 for HF. You'll have plus 0.92 times 2725.3 for Hg, and then minus the 561 again. Units for these things are kilojoules per kilogram. So your H2 is 2552.2 kilojoules per kilogram. For the entropy, you're going to do the same thing. So now you'll have SF2 plus X2 times SG2 minus SF2. Now when you get your values, you get 1.6718 plus 0.92 times 6.9919, whoops, not sure what that is, minus 1.6718. So now you get 6.5663 kilojoules per kilogram Kelvin. Then finally, we get to state 3. State 3 is over here, it's saturated liquid. So that value is in the table. So here, for H3, you look it up, at a pressure of 3 bar, the F point is going to be 561.47, which we had before. And then for S, you already have that, it's 1.678. and that's kilojoule per kilogram Kelvin. Now we finally have all of the numbers we need. Right, so now we can take all of these numbers, whoops, and we can plug them in up here. Now, let's see, I'm running out of room here. So let's call this equation 1. So from equation 1, we are going to have m2 dot equal to 80 kilograms per second. Multiply that by 561.47 minus the 150.86. Put that over 2552.2 minus 150.86. That is going to end up giving you 13.68 kilograms per second. Notice I left these units off. It's because they're going to cancel each other out. This is m2 dot. Now you can go ahead and find m1 dot because we had this relationship here. We know m3 dot. Now we found m2 dot. That'll give us m1 dot. So m1 dot is going to be 80 minus 13.68, which is 66.32 kilograms per second. Now finally we're able to take these mass flow rates and go up to this equation here. Alright, so when we plug in our values, we can see what we get. I'm going to turn this page over. Let's solve that equation for sigma dot. If we do that, we're going to have 80 kilograms per second times 1.6718 kilojoules per kilogram Kelvin. Then we're going to subtract 66.32 times 0.5188, and then subtract 13.68 times 6.5663. Now we've got that. And notice these units, I left them off, but the conversion we're going to need is 1 kilowatt per 1 kilojoule per second. Now what you're going to get with that is your kilograms. It's going to go away out of each of these, and what we're left with is a sigma dot of 9.51 kilowatts per Kelvin. Alright, and it's kilowatts because if you look, we've got kilojoules per second, so that goes to kilowatts, and then there's Kelvin. Alright, so these two terms have the same units as these right here. I was out of room though, so I didn't write them down, but that's what you get. So that's your rate of entropy production right there, 9.51 kilowatts per Kelvin.